Welcome to episode 6 of FRCode Academy. Today we'll be coding a teleoperated Swerve drivetrain from scratch in a command-based template. If you've been paying attention to the FRC scene, more and more teams are utilizing the Swerve drivetrain, especially at the competitive level. Of the last 3 World Championships, out of the 72 Einstein finalists, 100% of them were using Swerve. To keep up in modern FRC games, an efficient Swerve drive is mandatory. Swerve drives are made up of 4 Swerve modules, one module for each corner of the robot. Each module has a driving motor and a steering motor. The reason Swerve drives are so good is because in this configuration, each wheel can steer independently while maintaining full power. With some fancy code, we can get our robot to move in any direction, turn in place, and even turn while moving. Swerve drives offer complete freedom of motion, and it is our job as programmers to realize it. So let's get started. Many people have programmed Swerve drives before, so algorithms have been implemented into WPILib that do the complex calculations for us. We just need to know how to communicate with these algorithms, which is relatively simple to do. So let's go over some of their terminology and create a plan for how we're going to code this project. Chassis speed is how fast the entire chassis of our robot is moving in the 2D plane. It has an X, Y, and Z rotation component. We create chassis speed objects to declare how we want the robot to move based on our joystick inputs. The left joystick will map to the X and Y component of the chassis speed, and the right joystick will map to the rotation component. Once we have created our chassis speed object using our joystick inputs, we will plug it into the built-in WPILib Swerve module state algorithm. A Swerve module state is made up of 2 components, a Swerve module speed and a Swerve module's angle. Together they can represent every possible state that a Swerve module can be in. And what the built-in Swerve module state algorithm does is it computes the linear algebra and reverse kinematics required to give the 4 Swerve module states that equal the chassis speed. This is very important, so let's reiterate. If all 4 of the generated Swerve module states were true, if all the angles and speeds were actually happening, then the robot as a whole would be moving at the chassis speed. All that's left for us to do is apply the generated Swerve module states as quickly as possible, and we've created a fully functional teleoperated Swerve. This 4-step process is at the heart of every piece of Swerve code. Input to chassis speed to Swerve module states to apply to motors. Great, so let's begin to code it. First, we're going to create a new command-based project. We're going to need to import the Phoenix 6 library because we're using CTRE products. If you're using Neo or Neo Vortex Swerve, you're going to also have to download the Rev Robotics library. Now let's start coding the subsystem. We're going to have 4 identical Swerve modules, so we can make our code 1/4 the size by creating a Swerve module class and passing in the individual CAN IDs for all the motors and encoders. Each module is going to have a turn and drive motor, and it is going to have an absolute encoder. The Swerve drive I'm working on has Kraken motors for the turn and drive motors and CAN coders for the absolute encoders. So this Swerve module class may differ from your Swerve, but the rest of the logic will stay the same no matter what. Also, for each Swerve module class, we are going to create a turning PID controller. This is so we can adjust the wheel angle to match the Swerve module state. We can make the angle of the wheel instantly equal the Swerve module state, so we're going to make this PID controller to quickly and smoothly correct the angle of the wheel. Also, since Swerve module wheels are generally very light and frictionless, only a p-value for the PID controller is necessary. The default neutral mode config for Krakens is coast mode, which is bad because we want our motors to stay in place after we stop giving them current. So we're going to set them to brake mode. For reference, this is how easy it is to slide the wheels with coast mode on. And this is how hard it is to slide motors with brake mode on. This is preferable because when the wheels stay in place when no current is applied, it creates more predictable and precise movements. You don't have to worry about this for Neos because their default configuration is already brake mode. Now let's make a method that returns the angle of the Swerve module. The coordinate system of the FRC Swerve module is a little weird. 0 is at the top, pi and negative pi are at the bottom. So we're going to multiply by pi times 2 to convert to the FRC Swerve module coordinate system. Next, let's make a method to apply the Swerve module state. For the drive motor, we will just apply the speed, and for the angle motor, we will use a PID controller to set the angle. You may be wondering, how is this code going to work if you just apply the meters per second speed to the drive motor? Well, this is an implementation of open loop duty cycle control. Basically, we're not going to work with desired speeds, we're going to work with percent outputs. Whatever percent you move your joystick forward, say 50%, we will run the drive motors at 50% duty cycle. This type of control system has many advantages. Firstly, it is very simple to implement. It has next to no latency when applying speeds. Also, by not being rooted in any real-world units, there is no tuning required. Okay, now back to the Swerve subsystem. We will plug in all of the CANID constants. And we will create a drive method that takes in a chassis speed object, turns it into Swerve module states, and applies them. Let's use the method toSwerveModuleStates. This is the pre-built algorithm I talked about that transforms chassis speeds into Swerve module states. Notice it takes in one extra parameter, a Swerve drive kinematics object. Swerve kinematics just tells the method the dimensions of our Swerve drive. Sometimes, when combining speed and turn, the toSwerveModuleStates method will output a Swerve module state that goes faster than is possible for our Swerve drives to achieve. If left unchecked, only the motor that goes faster than a limit will be reduced, and we will lose control of our robot. What we need to do is proportionally reduce all of the motor's speed until they fall under the max limit. We can do that with the desaturate wheel speed method, and since we're using open loop duty cycle control, the maximum our motors can go is 100%. Now just apply them to our motors, and boom, we finished our Swerve subsystem. Now let's create our FRCode drive command. It will take in a controller and a Swerve subsystem. We will never want to stop controlling the robot, so we're only going to modify the execute method. We will get the joystick percentages for the X, Y, and Z rotation. We will apply what is called a deadband to the joystick percentages. Most joysticks are not 100% precise, and drift a little bit when given no input. This drift will be translated to our robot, which is annoying and can wear out the motors. So we will get rid of the joystick inputs below the deadband level. You will have to tune this based on your joystick. For joysticks that are very precise, you can have a low deadband level, which allows you to do small movements easily. For imprecise joysticks, you will need a higher deadband to eliminate drifting. Now we will multiply our joystick inputs by what max percent you want to control your Swerve by. If it is your first time driving Swerve, you should set a lower percentage so you don't accidentally break anything when crashing into a wall. For reference, all of the footage shot for this video, I was running Swerve at 20% full power. Now to achieve open loop duty cycle control, we can't just multiply by a number for the Z rotation, because the chassis speed takes in radians per second Z rotation, not meters per second Z rotation. So we have to do a little geometry to transform our desired percent rotation into the equivalent radians per second rotation. Make sure to multiply by our specially formulated Z offset instead of our Z percent. Now we call Swerve.drive with our newly created chassis speed object, and we're done. Now just put the Swerve subsystem, controller, and FRCode drive command into our robot container, and get ready to start dominating FRC competitions. Let's test out our code. That didn't seem to work correctly. What could be wrong with our code? Let's turn the robot on its side to see what's going on with its motors. It looks like our controller is accurately applying Swerve module states, but all of the wheels are pointing in completely random directions. This bug, as it turns out, is not the fault of our code. It is the fault of how the absolute encoders were mounted. For popular absolute encoders, such as CAN coders, it is very difficult to figure out the orientation of the magnet because it has no markings, and it is simpler to assemble it randomly and correct it within our code. So to get our Swerve code to work correctly, we'll need to add offsets for all of the wheels. So let's figure out the offset values. We need to manually read data from the absolute encoders, so turn them from private to public, and in the Swerve subsystem, from the periodic method, put the readings into the FRC dashboard of your choosing. I'm using the old shuffleboard, but you might be using Elastic or Advantage Scope, which both work just fine. Also, comment out the FRCode drive command in the robot container so that you don't accidentally hurt yourself when touching the wheels. You can also set the steer motor to coast mode, which will make it easier to adjust the wheels. Now deploy this new robot code, and for this next part, you're going to want the robot on blocks or on its side. Before you touch the wheels, attempt to drive the robot normally with the controller to make sure they can't move on their own. Okay, now adjust all of the wheels to be facing forward, and take notes on all of the encoder readings. These will be our wheel offsets, because at these readings, we know the wheel is actually at the 0 heading. Also, to tell if the wheel is facing forward, look at the bevel gears and make sure all of them are facing right. If the bevel gears are facing left, the wheel is actually pointing straight backward instead of straight forward. Amazing, now we can power off and fix our code. Obviously, we're going to turn brake mode back on for the steering motor and uncomment our FRCode drive command. Now for the fix, we'll open our constants file and add all of the motor offsets. We will pass them into each Swerve module, and we will subtract the read value by our offset value. This may make the reading go outside of the -pi to pi range, so we will add a quick if-else statement that will constrain it to the range. If you're feeling really fancy, you can do the same thing with the math.iee remainder method, which only takes one line. Now let's test out our code. We finally have a functional Swerve! But you may notice it's a little clunky to drive around. If you were to give Swerve in this state to your drive team, they would almost certainly curse you out for your terrible code. There are some important optimizations we need to make before we call it a day. The simplest and most critical optimization we can make is telling our PID controller that our coordinate system is not linear. Currently, the PID controller thinks the Swerve module is in a linear coordinate system, meaning that if the wheel is at 3 radians, and we suddenly desire -3 radians, it will go all the way around instead of jumping the gap, because it does not know that -pi and pi are connected. To fix this issue, all we need is a single line of code in our constructor telling our PID controller that its input is continuous. Now our Swerve module can jump the -pi to pi gap no problem. Another way we can optimize the PID path is by utilizing the reverse direction of the driving motor. Imagine a scenario where the wheel is currently at 0 degrees and we want to get to 160 degrees. We could turn 160 degrees to get there, or we could turn the opposite direction for only 20 degrees and reverse the direction our wheel spins. This would be much quicker and make it so that we would never have to turn more than 90 degrees at a time, because it'll utilize both sides of the wheel. Luckily, the WPI library already has a method to find these optimizations for Swerve module states. So again, we only need one line of code to make this optimization. The benefits can especially be seen when we turn in place. Without the optimization, our wheels will turn a full 180 degrees to switch their direction. But with the optimization, they don't turn at all. Instead, the motors are all run in reverse. Now that our Swerve is driving smoothly, it's time to make our final optimization. In its current state, it's very difficult to turn while moving. This is because all desired chassis speeds are given relative to the robot's heading, which constantly changes when you're spinning. A much more intuitive way of controlling the robot is giving its inputs relative to the field, because then, no matter which orientation the robot is in, a forward input will make the robot go forward in the field. So let's code it. We're going to instantiate a gyroscope in your Swerve subsystem. I'm using the popular and very reliable Pigeon 2.0. The reason we need a gyroscope is because we need something to keep track of the robot's heading, so we know exactly how much to offset the chassis speed. Make a method to get the heading of the robot from your gyroscope. Also, make a method to reset your gyroscope. This will redefine the field coordinates to whichever direction the robot's front is facing. Now go to the arcade drive command. We will use the built-in WPI library method from field relative speeds, which gives us the robot relative chassis speed that takes into account the heading of the robot. This enables field-oriented drive. We still might want to use robot-oriented drive in specific scenarios, so we will make it available with a toggle of the right bumper. But the default will always be field-oriented drive. Now make an instant command that will reset the heading of the gyroscope. Put it inside the robot container and map it to the left bumper. And congratulations, you programmed a fully functional, teleoperated Swerve drive. Let's try it out. You can drive it in the field-oriented drive and robot-oriented drive whenever you want. Also, you can use the reset button to redefine which way is forward. And because it's designed with open loop duty cycle control, it's trivial to change the speed at which it operates. You can make it run at 10% power to make it super safe for anybody to test out and drive. Or you can make it run at a 100% power, so you suck every last bit of speed out of your motors for competitions. Or you could set the turn to 100% and the speeds to 10%, turning your Swerve into a Beyblade. Or if you're mentally insane, you could set the Y speed to 0, hold the robot-oriented button, and transform your Swerve into a tank drive. Coding Swerve with open loop duty cycle control gives you complete power over your Swerve drive. Unfortunately, that'll be all for this video. If you want to learn how to program an autonomous routine for Swerve drives, you can watch episode 7. This has been Victor Moldavanu from Team 612. See you later, and goodbye.